Good morning, everyone, and welcome to Autodesk Virtual Academy, brought to you by KETIV Technologies. I'm Nigel, and by Customer Success Manager here at KETIV Technologies, and I'm joined by Nikhil Venkat. How's it going, Nikhil?
Pretty good. How are you, Nigel?
Good. So Nikhil is one of our simulation experts here on the team. He has a lot of experience in FEA analyses, even doing hand calculations, which are my least favorite thing in the world. I do love my quadruple integrals. So today we're going to be going over something really cool in Nastran In-CAD, and that's stress linearization. And don't worry if you don't know what that is. Nikhil will explain that for you. I know he had to explain it to me for me to find out what it was. So it's something new that was in a recent addition to In-CAD, which is the 2019.1 release, if I remember correctly. And we want to make sure that everyone's aware of what's available in the tools, and that's part of why we do Autodesk Virtual Academy in the first place. So with that, I think my explanation of stress linearization is nowhere close to what it's going to be from Nikhil here. So what I'll do is I'll let him take over from here. But
thanks, Nigel. Nikhil, by the way.
Yeah.
So as Nigel mentioned, today we're going to be talking about stress linearization. It's something that was just added into Nastran In-CAD in the 2019.1 release. So we want to go over some basic things about what is stress linearization, why is it important, how do we essentially do stress linearization, how do we linearize stresses, how do we get the results that we would expect, and then we'll go over some questions which hopefully we can provide answers immediately. So first of all, stress linearization is something that you will see available in the Nastran In-CAD 2019.1 release, which was the most recent one, the most recent update. It released in July of this year, a couple of months ago. So in case if you have installed the update, then you will see a giant stress linearization button right in the middle of your results panel. You should not miss that. So in case you haven't installed it, then you can go into your desktop app, or you can go into your Autodesk portal, and you should be able to find the update there and install it. And if you haven't upgraded to 2019 just yet, then here's the reason to do so. This, by the way, I have to mention, is just one of the things that's new in the 2019.1 release. You have a few other new features as well that make In-CAD much more user-friendly and a lot easier to use now. So I would recommend going and exploring that as well. But the stress linearization, essentially, it is the separation of stresses through an actual thickness into membrane, or into constant membrane stresses or average stresses, and bending stresses, so that the net force and moment across the thickness remains the same as that due to actual stress distribution. It's used typically to comply with design codes and requirements of the pressure vessel industry. You can use the stress linearization utility to graph local stress tensors along a linear path, and/or determine the relative contributions of bending and membrane stress for any kind of structure. The two different methods of determining the membrane and bending stresses, one being based on the maximum shear stress, the other one being based on the von Mises stress, and Nastran In-CAD calculates and displays results based on both methods. It's also worth remembering that while the lion's share of the application is for pressure vessels, it's not limited to pressure vessels. In fact, you can linearize stresses through any structure as long as it makes sense to do so, by which I mean as long as it makes sense to extract separate bending and membrane stresses. Now, stress linearization utility, it graphs, as we mentioned, it graphs the specified stress tensors along what is called a stress classification line. Now, this stress classification line is user-defined, and it is a straight line that runs from the inside to the outside of the vessel. FEA provides the raw stress data at nodes along this line. What the stress linearization tool does is it takes the nodal data for this complex stress pattern and breaks it down into components. So those components, as we mentioned already, are membrane stresses, bending stresses, membrane and bending stresses, which is the sum of the two numbers, and the ASME code allows the membrane bending stress to be higher than the membrane stress itself. And also the peak stress. The peak stress is the highest stress found along that stress classification line. This is always positive, but not necessarily higher than the membrane plus bending number. Peak stress is something that you would usually use to determine the fatigue life at this stress classification line. So, excuse me, it's important to remember and understand what each of these stress components, these linearized stress components, refer to and what they're actually doing. Now you see this image on your screen. That just describes the different kinds of stresses. So you have your stress classification line, or the tangential stress. Rather, the SCL is along the tangential stress line. You have the hoop stress, which is either into or out of the plane, and you have the normal stress, which you can of course determine. Rather, you can determine the hoop stress once you have the normal and tangential stresses using the right-hand rule. Now, why is this important? It is important because linearized stresses is what you have to compare to the standards and the requirements in the ASME boiler and pressure vessel code. So the ASME pressure vessel code is based on the observed safety of vessels. It is a real-world working standard which specify minimum requirements for design, materials, fabrication, and testing of pressure vessels. And the way that this code was developed was almost completely empirical. So its roots were born of failed pressure vessels much before stress concentration was even understood, and the concept of stress concentration was even understood. So at the start of the code, people ran out of theoretical explanations when objects when designs got more complex in simple cylinders and spheres. So when further rules were required for items like flanged and dished heads, they actually built full-sized vessels and models and tested them. And the observations, they did this a number of times, and the observations were then turned into a set of design rules. Vessels did eventually become safer through these efforts. So what it actually gives you, what the ASME pressure code gives you, is a breakdown of primary stresses, secondary stresses, and peak stresses, as we already talked about. Primary stresses are the general membrane stresses, local membrane stresses, and the bending stresses separately. The secondary stresses are an addition of all these, a sum of all these, and the peak stresses, of course, are the highest stresses. Peak stresses are the highest stresses along the SCL, which you would use for fatigue life. You also have sections that are called design by rule or design by formulae. So that's, if you're using these rules directly, if you're using hand calcs, as Nigel mentioned, being his favorite part.
Oh, yeah.
If you're using that, you have separate codes for that. And if you're using FEA, then you have a design by analysis section, which is what we would be interested in. Now, as we mentioned earlier, the ASME boiler and pressure vessel code, just like stress linearization, doesn't just talk about the pressure vessel shell. It also talks about flanges, it talks about welds, it talks about a whole bunch of things. So if that's something that you're interested in, then there's a specific way that you would analyze that. So if you're interested in best practices about welds, or anything of that sort, then please feel free to
Call Nikhil.
Yep, contact us, contact Nigel, contact me. One of us will be able to help you. Now, I did mention that a lot of this, a lot of the empirical design rules help make designs safer. Now, that's not an absolute statement, because as recently as 2002, this data is from 2002. This data was taken from the National Board of Boiler and Pressure Vessel Inspectors, their bulletin from summer 2003. As you can see, what's highlighted in red talks about the frequency of faulty design or fabrication, and somewhere in the text they actually mention that most of this, even the fabrication errors, most of them can be attributed to design errors. So even though we have a set of acceptable standards, there is no silver bullet, I guess, to get a design right. So it's important to understand exactly what you're doing, exactly what you're analyzing, in order to make sure that you don't have faulty designs, you don't have catastrophic failures. And some of these numbers, especially when it involves heat, you look at a total of 100 and something accidents a year, and that's fairly concerning, because that says we're looking at 10 accidents a month on average, which is fairly concerning. This is the last time, by the way, they released a breakdown of data like this. So the hope is that these statistics have improved and we don't have nearly as many failures or errors today. So let's jump into Nastran In-CAD real quick. So can you see my screen?
Yeah, we'll just double check and we're good to go.
Perfect. So this is a simple low down pressure vessel. So it has 4 legs and it has a bunch of nozzles, pressure head, apologize. Now, to make this easier, we have cut this model in half. That's just to make the analysis quicker and everything. And we're going to be using a symmetric model. So I'm going to jump into Nastran In-CAD here real quick. And so I have some mesh settings set up already. Just going to go and mesh that quickly, if it does.
Cool. And while we're waiting for all of this to run to Nikhil, if anyone has any questions during any of this, or we're going too fast, please let us know, and we'll either slow down, reiterate something. Yeah, so on and so forth.
Okay, so we want to set this up. It's a very simple setup. We're just looking at a simple pressure test on this. So for constraints, I want to fix the 2 legs. I'm also going to cheat a little bit here and fix that edge there. That in truth is not exactly fixed, but it is held in place. Just to make our life easier, we're going to fix that completely. And as we mentioned already, this is a symmetric model, so we have to account for that symmetry. So this is symmetric about the z-axis. It's going to select all of those surfaces, those cut surfaces. So those, that surface there, that one. I think that's all of them. Yep, looks like all of them. Now for loads, we don't really care about the flanges. I'm only interested in the shell. I'm going to use a fairly small load, 5 megapascals, which roughly is 750 psi. So I'm just going to analyze the shell itself, and I don't really care about anything else, the flanges or any attachments. We're using steel for this, although, again, I understand general practice is to use something much stronger than steel, so super duplex maybe. But for the sake of this problem, we're just going to use steel. I'm going to go ahead and run the model.
Ooh, and while that's running, it's going to take a little bit to run that guy. Go ahead and ask any questions while we're doing this. We have about 30 seconds to a minute to do so. Stephen asks, you're running this on a part file. Is there any difference or reason why you're running it as a part rather than like an assembly?
Yes. The only thing is simplicity, because if we're running it as an assembly, then we will have to specify contacts between the different mating components, and it adds to complexity, it adds to solve time. So in this case, since we're just doing a quick example, I figured it was easier to just combine the whole thing into one single part, assume that the whole thing is bonded, and run it that way.
Yep. In some cases, obviously, you're going to want to run your analysis on an assembly based on what kind of thing you're trying to solve, right? If there's motion between two components, probably going to want to do that. When it's like things like bolted connections, probably going to want to do that as well. Let's see. Before this is done, another question from Curtis. Why are you applying the pressure to the outside surface and not the inside surfaces? Any particular reason?
No particular reason. Again, we're just looking at the strength of the shell itself. So again, the pressure code I know calls for internal pressure, because again that's what this pressure vessel does. But we're not actually following the code. The idea is to figure out how we can use stress linearization and how we can correlate that with the code. So I suppose it's just more it's just easier visually. It's easier to understand with the compression as opposed to expansion. Okay, so this is what I mean, by the way. You have this giant stress linearization button, which you absolutely cannot miss. So since we fixed this, we have this edge being held down and the rest of it essentially getting crushed, getting crumpled. I want to make this a little better visually. So turn off, actually I'll keep element edges on. Turn off loads and constraints. You can also turn it off in here, by the way. So if you look at our stress results, since we have used solid elements, we have solid normal stresses in different directions, we have shear stresses along different directions, we have principal stresses, but we don't actually have bending and membrane stresses, right? And the von Mises stress doesn't actually give us that information. So we're going to have to linearize the stress. Right, so if I hit the stress linearization button, second, go. So this is the stress linearization dialog. The idea is to define the stress classification line, which is along the tangential stress line, and then define either an n-axis, a normal line, or an h-axis, a hoop line, the hoop axis. So for the first point in the stress linearization, I want to pick a point on the inside. You can do this in three ways. You can either enter the coordinates of the point itself, or you can enter the node number if you know it, however unlikely that may be, or you can just select that, make sure your cursor that box is active, just go in and click, and it's going to automatically capture that node number. The last point, again, keep in mind that this is the SCL, this is the tangential stress line. I'm going to pick a point on there. And now we need, actually, let's pick a point there. Okay. And now we need a normal point. So I'm just going to pick that. So you also have the number of divisions. So if you want a smoother curve, for example, you can increase the number of divisions if that helps you in any way. But now up here you can see the different tensors. So this is the normal tensor, the tangential, hoop, normal and tangential, and so on. This gives you a good idea of what you should be looking at in terms of stresses, because at the end, these are the numbers that you want to be comparing with the pressure code. The PM refers to the principal membrane stress, principal bending, principal membrane plus principal bending. This is based on shear stress, and based on 1 Mises, again, membrane bending, membrane plus bending. So you can also export this to a CSV file. So I'm just going to say pressure vessel data. So if we open that up, you'll see that now we have these results. We have the 1 Mises stress results. We have the shear stress results based on the results that we have in here. It tells you the reference points. The point defines the n-axis, the normal axis, and so on. So this is a convenient CSV file that you can use going forward. Now, you could say, well, I have seen membrane stresses in Nastran In-CAD before. I can use shell elements and get a membrane stress, and that would make total sense. It would make total sense, and you can use a shell element almost through the midplane of this, and assign a thickness to that, and go from there. A couple of issues with that. One being, potentially, you could potentially have certain components that cannot be shelled, or that can be shelled but don't necessarily make sense to be shelled. So in those cases, you're going to have to connect the shell to the solid elements, which is never ideal. And secondly, the way membrane stresses on a shell element are calculated is very different than membrane stresses extrapolated from solid element results. So you will see some difference in results, and again, that's not really an apples to apples comparison with the pressure code. The entire idea behind this is to make sure that you have that apples to apples comparison. You're always looking at it on the same scale, so you can define your safety factors, etc. So that's the concept of stress linearization. Any questions?
Yeah, so there's definitely a couple of questions, and I think some of these can be answered with some of the previous videos that we've done.
Mm-hmm.
First off, is there a particular recommendation for number of elements, specifically solid elements, in a through thickness direction?
In a through thickness direction? So I'm
assuming like
I think it's through the thickness here.
Yeah.
You want at least one element. I think most of the time the meshing engine forces you to have at least one element in there. It fails otherwise. So you would want at least one element, but again, it depends on what you're expecting to happen through this thickness, right? If you have some very different behavior from one end to the other, then yes, you do want a large number of elements to capture that. If not, and you're just expecting the behavior to be more uniform, then yes, 1 or 2 elements is going to be fine.
Yeah, it really depends, right? When you're looking at like solid structures or whatever, in regards to meshing, any areas of note is what I like to say in the particular model itself. Any areas of note where you're expecting something weird to happen, or you're expecting a very large difference between one side and the other side of a particular surface, you're going to want more elements, right? But for here, we're expecting pretty uniform, deformation and stress across the entire surface. So you don't need to necessarily increase the mesh number for that. But if we were doing something like, like a static bend test on a particular thing, obviously you're going to want more elements depending on what you're doing. So.
And just to add to that, one of the considerations is, of course, the element size. So the general element size we've used is 20 millimeters, and the height of this is roughly 2,500 millimeters. We already have 131,000 elements in here. So if you say wanted 3 or 4 elements through the thickness, then that is going to drive up the element count pretty 3, 4, 5,
6-fold. Yeah, it's going to be
crazy. So you have all of these different considerations, and it's always a trade-off.
Yep, there is always the trade-off. So what I like to do, right, is when I first start doing some simulations, some design validation of my particular design, go ahead and go with like maybe a more coarse element size to start out with, right? And just, run your analysis. And if you see what's expected, right, it's like, I'm apply a load here. If there's a deformation in that area, sure, that's expected. But if there's a deformation somewhere completely different than what you expected to happen, then maybe start, driving the mesh finer and finer and figuring out exactly what's going on. You don't want to start running the most fine mesh possible. I made this mistake when I was learning all this stuff in college. I was like, oh, I'm just going to skip all of these design or these, simulation iterations. I'm just going to make, 4 million elements, and I'm going to run this thing for 15 hours, and hopefully I get the right answer. And we talked about this in a couple of AVAs ago, right? There's a stage in which increasing the amount of elements is not going to increase the, the validity of your results. You're going to hit this plateau, and, increasing the elements, but beyond that are going to give you, reducing gains, right? So what else do we got? Can you run internal expansion to compare the results as well? Because we did compression on this guy. So yeah, it's the same thing, right? You just apply the loads in the other place.
Different locations, yes.
Yeah.
So I'm going to get rid of those. Just apply loads there.
On the inside.
On the inside instead.
And same thing on the bottom.
Same thing on the bottom.
Yep, and you just run the same simulation, and you can look at it that way too.
Yeah.
So with that, I think that should be it for everything today. We'll see you again next week, everyone next time. Same time, same place, Thursday morning at 10 for iLogic 101 next week. So thanks everybody for attending, and we'll see you then.
Thanks, everyone.